Hello everybody, Namaskar and good day to all. Hope the day 1 and day 2 program followed the synapses and then you have gone through the assignments shared with you. Day 3. Day 2 we ended with a concept on dipole, and day 3 will continue with the same concept of dipole. Very popular examples you can expect in the exams. Now, it is the case of dipole placed in external uniform field. So this is a dipole whose dipole moment is P bar, placed in an external uniform electric field of intensity E bar. Now, each of the charges will experience a force by principle. The positive charge, a force along the field, which is nothing but E times Q. This force on the positive charge you can see along the field, and this force on the negative charge E is opposite to the field. Now here, this dipole I have placed at an angle theta. That is, the angle between P bar and E bar vector is theta. Now, two equal and opposite forces we can see on the dipole. Positive charge and negative charge equal and opposite forces. Therefore, the net force is 0. Net force 0 means no translatory motion acquired by the dipole in the external uniform electric field. But now you can see these forces on positive and negative charges, they form a couple because equal, opposite along different lines of action, therefore it form a couple. Now, as a consequence of the couple, you will find the torque on the couple. Torque on the couple given by this dipole moment P bar cross E bar. This is not the algebraic product. You can see here this is a cross product of vectors. Tau bar, the torque vector is P bar cross E bar, and this order is very essential in the cross product. Now, because of this torque, dipole will acquire a rotatory motion. Now it tends to rotate about this point axis, this kind of axis, and it acquires a torque and hence acquires rotatory motion. Therefore, dipole in an external uniform electric field, no translatory motion, and it acquires only rotatory motion due to this torque, and torque aligns the dipole in the direction of external field. Now I am writing the magnitude of the torque, this cross product, which will be equal to P E sin theta, dipole moment, intensity of the external field, and of course theta is the angle between P bar and E bar shown in the figure. Now you will find that for theta is equal to 0. Theta equal to 0 means in the direction of field, if it is placed, torque is 0. Now torque 0 means it is called rotational equilibrium. Rotational equilibrium, and that is called as stable equilibrium. For theta is equal to 180 degree also, sin theta becomes 0, and one more time torque becomes 0. So again a rotational equilibrium, but it is called unstable equilibrium. Remember, theta equal to 0 position is called stable equilibrium, and theta is equal to 180 degrees is called unstable equilibrium. And of course, for theta is equal to 90, that is, if we place the dipole at right angles to the electric field, torque becomes maximum. So maximum torque for theta is equal to 90 degrees, and the minimum, that is 0 for the two cases of 0 degrees and 180 degrees. For any other different angles that are given, you can just substitute and get your answers, right? So this is one important point for dipole. Now let us come to another concept for the same dipole placed in uniform electric field. It will acquire potential energy. It will acquire potential energy, and that is given by this. I am represented by U. Electrostatic potential energy equal to, this is a negative sign, negative of dot product P bar dipole moment vector and E bar intensity vector. So this is minus PE cos theta. Remember, potential energy should always be used here along with negative sign. Now here again I am showing few results. For theta is equal to 180 degrees, which we earlier called as unstable equilibrium. Cos 180 becomes minus 1, therefore this entire term becomes plus PE. And this is the maximum potential energy in unstable equilibrium position, and minimum potential energy for theta is equal to 0 degrees, that is stable equilibrium position. It is minimum potential energy, and this is minus PE. One more case also, you remember that for theta is equal to 90 degrees. 90 degrees means it is experiencing maximum torque in that position. For that position you will find U is equal to 0. But remember, U equal to 0 is not minimum. This case you remember as a very special case, because many a times this any parameter acquiring 0, we take it as the minimum condition. But in some conditions, see for example in this case, U is 0, but it is not minimum. Minimum is minus P, you can find here, right? Now, one more example in the case of electric dipole is dipole placed in external electric field, and then it is turned, rotated against the torque. So the keyword is dipole in external field and turned against torque. Alright. So for the dipole rotated in external field, work is to be done because it is against torque. So work is done. That work will store as potential energy. Now the change in potential energy is now nothing but work. So here I am writing work done for the rotation of dipole as negative of, again this negative term shows that it is against torque. So negative P times, supposing I have rotated this dipole from initial angle theta 1 to final angle theta 2. In that case, this work done is minus PE terms cos theta 1 minus cos theta 2. Right? You can see this. This is cos theta 1 minus cos theta 2. Theta 1 position to theta 2 position. Now, most of the times you are given that the dipole is turned from its equilibrium position. From its equilibrium position to 30 degrees, 60 degrees in such examples, that is theta 1 becomes 0 equilibrium position, then it becomes cos theta 1 becomes cos 0 1. So minus P times 1 minus cos theta, right? So one more another important concept would be charged particle projected, thrown in external electric field. So with certain initial velocity, the particle is projected in external uniform electric field. Again here I am discussing the three cases. Suppose the case 1, theta equal to 0 degrees. The charged particle projected along the electric field. In such case, yesterday's definition you will remember, F is equal to EQ and the direction also. So because of that, if it is a positive charge projected parallel to the electric field, it accelerates, that is velocity increases and gains kinetic energy. So it is acceleration and gain of kinetic energy for positive charge, whereas for negative charge projected along parallel the electric field, it will acquire retardation. It retards, velocity decreases, and therefore it is loss of kinetic energy. Now this loss of kinetic energy in this case is given by work energy theorem. Delta K, the loss of kinetic energy is equal to the loss or gain. I am again telling you this is the change in potential energy. In this case it is gain, in this case it is loss. So in general, the change in kinetic energy is E, the field strength, Q, the charge projected, and S is the displacement. This will give us the change in potential, the change in kinetic energy. Now if it is the other case, like theta is equal to 180 degrees, exactly the reverse will take place. That is positive charge retards and loss of kinetic energy, right? Negative charge accelerates and gains kinetic energy. So the important point is to see whether it is a positive charge or negative charge that is projected. Now one more case I am showing you there. For theta is equal to 90 degrees. See here, theta equal to 90 degree case. Now here I have shown first for a positive charge projected normal to the electric field, perpendicular to the electric field. Then the path will be a parabola. Path will be parabola. Please do remember, in the case of theta equal to 0 degrees or 180 degrees, the path is a straight line. Path is straight line, but with increasing velocity or decreasing velocity. Whereas for theta is other than 0 or 180, the path will be parabola. The path will be parabola such that you can also please careful about the charge. Positive charge, I am writing a parabola in the direction of electric field. Whereas if it is a negative charge, since the force is anti-parallel to the field, now it is negative charge I have shown, and the parabola will take this, that is opposite to the trajectory. You will find opposite to the electric field, whereas the trajectory for positive charge will find it in the direction of electric field. So for a particle like electron, it will be a path, the trajectory opposite to the field, and any particle such as proton or alpha particle, the trajectory is along the field. Now let us see the electric field intensity produced by continuous charge distribution. Few important cases for our NEET and CET. Now to begin with, I have taken line of charge. In fact, it is a long line of charge. A wire which is charged like that. Now here I have shown, it's a long wire, I have not shown the ends. It's a long wire and it is charged such that linear charge density is lambda. I am writing lambda here refers to charge per unit length, linear charge density. Now in this case, P is a point. Carefully watch this point P, and this point P is a lateral point. It is not a point along the side. For any point along the side, supposing if I consider a point over here, then intensity at this point is not defined, it is 0, right? Therefore, we are defining intensity at a lateral point. At the lateral point, you will see here, this intensity at the point P is lambda by 2 pi epsilon naught r. Lambda for charge per unit length. This is an expression. And remember, here you will find that E proportional to 1 by r. In the case of point charge, it was E proportional to 1 by r square. In the case of short dipole, it was E proportional to 1 by r cube. Now here you will find another result, that E proportional to 1 by r. Now another example for continuous charge distribution would be conducting sheet of charge. Now this time I have taken a sheet of charge, and remember it's a conducting sheet of charge. It is charged such that charge per unit area surface charge density I have taken it as sigma. So sigma is the surface charge density. So here again it's a long sheet of charge, and here I have shown the point P, which is at a distance r. Now at this point P, the intensity is a quite interesting result. EP is equal to sigma by 2 epsilon naught. You will find this expression is independent of the distance term, E proportional to R raised to 0, I have written, right? Independent of distance, what does it mean? Whether it is a point at a distance of 5 centimeter or a point at 10 centimeter, intensity is same at each and every point, which means that the electric field produced by a sheet of charge is a uniform electric field, right? So this is an example for uniform electric field. In all the other cases that we have seen, it was non-uniform electric field, intensity and magnitude changing at different distances. Of course, not to forget about the direction. Now here in this case, if it is the point P at a distance R, the intensity vector I will show here as a vector S like this. Means if it is a positively charged line, I am writing it as a vector normal to the line and away from positive charge. If it is a negative charge, the same will be normal and towards the line of charge we will get. Now in this case also, earlier we have taken it is sigma by 2 epsilon naught is the intensity magnitude, and if we have to write the direction, it is again normal to the sheet. Do remember, this is sheet. Sheet is imagined like this. Now this is a vector I am writing. This is a vector I am writing. If this is what is the sheet of charge, this is what is the intensity vector. Normal to the sheet, away from positive charge. See, here positive charge is shown and it is away from the sheet. And if it is the same negative charge, it will be like normal to the sheet and towards the sheet it becomes. This vector is very important because, see, I show you one simple example. Supposing I have a case where these are two sheets, both are charged such that it is plus sigma 1, positively charged. This one supposing I give minus sigma 2, negatively charged sheet. Here I have shown unlike charges. It can be either unlike charges or like charges, and a point is given over here. This is point P at which I want the net intensity. Then in the very introductory point we have told that intensity is a vector quantity. So whenever intensity examples we come across, vector notation is very, very, very important. Never forget that. Therefore here first we have to write the vectors. Due to sigma 1, that is what is E1 is equal to sigma 1 by 2 epsilon naught, it will be this vector. I am writing this one, the vector E1, and due to sigma 2 also we get E2. The E2 will also be in the same direction. Why? Because earlier we have told negative charge means normal and towards the sheet. If it is positive charge, it is normal and away from sheet. Therefore E2 is sigma 2 by 2 epsilon naught, where you will find that both E1 bar and E2 bar are parallel. Because of this, so what will be the net intensity? It will be E1 plus E2. You have to take summation E1 plus E2. This plus is due to the vector addition. It is not the algebraic addition we have taken. And therefore, if it is supposing, in some example you will get it as E1 minus E2. Supposing you got E1 minus E2. Now there is a confusion. There is a confusion or there is a chance for committing a simple mistake that E1 is sigma 1, which is positive by 2 epsilon naught. Suppose E2 is minus sigma 2 by 2 epsilon naught. Okay. Now suppose if they are anti-parallel, E1 bar opposite to E2 bar. In this case, what is the net intensity? Because this opposite direction, you will get it as E1 minus E2. Now here, a simple mistake is committed that this is sigma 1 by 2 epsilon naught minus of minus sigma 2 by 2 epsilon naught, and finally you will write it as negative of negative positive. It should not happen here. So in the case of intensity, that is, which is a vector quantity, when we are doing such plus or minus, it is not the algebraic addition, it is a vector addition. Therefore negative sign given to the charge should never be carried into the examples. Therefore here it will be simply no negative sign, though it is given as sigma 2 is negative. In the calculation the negative sign should not carry. Not only in this example, in any of the system of charges, and the case of finding net intensity, the negative sign given to the charge never carries into the calculation. There the positive sign or negative sign, the plus minus is only due to the vector addition. Please do remember. One more a very popular case of continuous charge distribution would be, see, charged conducting sphere. I am taking whether it is sphere or shell, the results are same, because when a sphere is charged due to the property of expulsion, all the charge will completely distribute only on surface, no net charge inside the sphere. Therefore, if it is a charged conducting sphere or shell, the results are the same. Here you see, I have shown a charged shell or a sphere. Radius of the sphere is capital R. The charge on this sphere is Q. Then Q charge by 4 pi r square, surface area becomes surface charge density. And here we will consider 3 different positions. See, this position P1, the point P1 is well inside point I have taken. P2 is a point on the surface and P3 is a point outside the surface. Now, in all the cases, the distances are always taken from the center, whether it is P1 or P3, the distance that you have taken, the D or R that I have shown, is always from the center. Supposing if you are given a distance from the surface, then what happens? Then you have to take small r equal to capital R plus x, whatever that is given from the surface. So make sure I am writing all these distances from the center. And in the given example, please make sure of that. Now here comes inside point. We have told no net charge inside the sphere, and therefore no flux, and hence intensity is 0. So any intensity, any inside point within the surface, the intensity is 0. Whereas on the surface, P2 I have taken a point on the surface for which you will find the intensity as 1 by 4 pi epsilon naught Q by R square. Q by R square, and do remember this is the maximum intensity produced by the shell or the charged sphere. So intensity is maximum on the surface. Here I have taken Q by 4 pi R square, the surface charge density. Therefore, alternate form also I have shown surface charge density by sigma naught. Right. Now I have taken outside point here. So you see here P3 is an outside point. P3 is a outside point, distance off from the center. Then it is 1 by 4 pi epsilon naught Q by R square. This also have given alternate form in terms of sigma. So it is sigma by capital R by small r, radius, distance of the point. And here, of course, there is a square term, you can see that. So in fact, these results show that when a shell or a conducting sphere is charged, though all the charge expels and resides only on the surface, but it now acts as a point charge, as if all the charge is focused at its center. So a shell or a conducting charge sphere acts as a point charge, seems to be apparently. Apparently they act as a point charge, because this result will show you the same was the result for even a point charge also, right? Now these results sometimes asked a graphical analysis. You can see here I have shown a simple graph, intensity versus distance from the center. So this x-axis is the distance term, y-axis is the intensity term. Now you will find r equal to 0 represents the center, r equal to minus r and r equal to plus r represents the surface, right? So from minus r to plus r, you will find the graph is completely discontinuous. There is no graph that you can find at r, from r equal to minus r to r equal to plus r. You have graph which is a parabola. It becomes, because of this result, you will find this E outside point is proportional to 1 by r square, right? And that is why after this small r equal to plus r or r equal to minus r, the graph you will get it as a parabola. Therefore, this is a discontinuous graph from r equal to minus r to r equal to plus r.